All right, so let's see what we have today. So far we got 3 tutorials, and for tutorial number 3 in the past Friday, it was about the doubling strategy, like how you can derive the asymptotic upper bound. So please take a look at that exercise there, and also task number 2 is about doing some comparison, okay? So you can look at the lecture site. I already put down the materials there. So it will be under right here, okay? That was week number 3. And we got task number 1 and task number 2. So task number 1 is about the mathematical derivation for the doubling strategy. And task number 2 is to really compare the 2 strategies. Okay? So that's something you want to dive into and make sure you can do the mathematical analysis. That might be something you will be asked to do, maybe partially or totally, right, during the test or exam. Okay, so that's about the tutorial. And I also updated the slides yesterday. So if you look at the self-balancing BST, so I just updated last night. So I think it would be pretty much stable. There might be a few more slides I might add, maybe before Wednesday. So I'll let you know if that's the case. But there's definitely more materials there. More like a background about insertion and deletion, because when we talk about tree rotation, tree rotations, you have to know how to do insertion deletion that cause the tree rotation. That's something I'll cover as well today to really build the context more complete. Okay, and then, okay, just about Wednesday, okay? So for Wednesday, just for this week, because I will finish, I'm also teaching 2030 at the same time, but they will finish their first programming test around 3:50. So I'll try to really run from Williamsburg Center as soon as it is done. But for me to come here and also set up, we might have some slight delay. Why don't we do the following? So we'll start the class on Wednesday at 4:10 p.m. I'll announce this as well on the e-class. And then I will go until maybe about 5:50-ish. I don't think there's any class after us. I don't think so. But in case it is, then we have to find other time. So if there's no class after us, maybe around 5. Sorry, keep getting myself confused. Around 5:20, I'll just pause. And then for those of you who may have to catch another class, you can feel free to go. I might just continue with another 10 or 15 minutes to make sure the time is complete. But you can also look at the tutorial, only for 10 minutes maximum, okay? So for Wednesday, we're gonna start the class slightly later, just for 10 minutes, okay? I'll try to really come back as soon as I can, but let's say 4:10, okay? So you don't have to wait for me for too long. I'll put this up on the e-class announcement for today, after today's class. All right, any questions about tutorial-ish, right? Again, you know, the tutorial exercises are required study materials. Make sure you go over them and also do them by yourself, okay? If you got any trouble, especially the mathematical analysis, amortized or average case analysis for doubling, please let me know. Okay, I will definitely can go over the steps with you. But I think the video solution I put up there is pretty detailed. That's something you really want to follow. The reasoning is very similar to the constant increments that we did in the class. Very similar, except that you got to use the log and geometrical sequence sum. That's the only difference. Okay, so quick recap, and then we'll move on with today's lecture. Okay. So what we got last time was, of course, we did the whole page right here about doing the mathematical analysis for amortized analysis. Okay, just very quickly, when we say amortized, it's really about average, okay? So you're gonna analyze a sequence of push operations, added up together for their running time, and then divided by the n pushes. It turns out the average is still big O of n. So it doesn't really help too much, even in the average case. However, in the tutorial, we actually show you that if you try to change the strategy from constant increments into doubling, you actually see some very promising change. So that's something you will have to study in detail, right? So that'll be the tutorial exercise you got to do. And then we spoke about, about the different visualization and also how we come up with, especially about how many resizing steps should we do exactly. So that'll be the K we want to calculate. So when you actually go over the exercise for doubling, you will need to calculate the K in a very similar way, except that now, when we go from resizing step to another, rather than adding some fixed constant, you're actually doubling the size of the array. So intuitively, in the doubling strategy, you're actually going to require strictly less or fewer resizing steps. So that's why it will turn out the fewer resizing steps you will have to do, the more efficient or cheaper it's going to be in the long term, right? So that's really the insight you want to gain from comparing these 2 strategies, okay? Any question in general about this exercise over here? Anything? Okay. This is really something you again, you want to somehow understand what's going on in the class, and then you want to really practice this, right? All the clean pages are made available to you. You really want to try them out, right? And make sure you understand all the details here. And then we spoke about, and then we try to derive the geometric sequence sum. So that's really necessary for the doubling strategy derivation. All right, okay. And then we switch to the new lecture, which we're going to continue today. So we talk about basically about the heights of the binary search tree. So this is simply some facts that we learned from 2101, you know, maybe from the winter, maybe from your previous term. The recap. Depending on how you exactly build a tree, there's no guarantee in general that the height of the binary search tree is going to be log n. That'll be the most ideal, of course, but not necessarily. Okay? So in the worst case, if you try to, for example, build a tree by inserting the keys value in this particular order, you're going to get very slanted tree in this way. Right? So that one is actually going to give you linear heights right here. Okay? I'll dive a little bit deeper into insertion and deletion today, just review the steps, because that's so necessary for you to understand. Otherwise, you wouldn't know how exactly rotation will actually happen. So that will be the first half. We're going to review this kind of stuff. In the second half, we'll do some rotation exercises, and then we'll continue the rest of the rotation, because there are different kinds of rotation you can do to restore the balance. So this page here, just make sure I understand the heights for the binary search tree may be linear in the worst case. So you got to be very careful. Okay, and then we talk about high balance property, right? So the high balance property, you will see the definition on the slides, right? Okay, so I'll just show you very quickly. Oh, actually, that's right here. The high balance property just defined as this. First of all, we know the heights. You want to review the definition for what's really the height of a particular node, depending on whether the node is either external, meaning that there's no further child nodes, or the node there is actually internal. You got at least one child node. How do we compute the heights? And then when we look at, for example, let's say this particular binary search tree, right? We're going to start with that. So in this particular implementation, we're going to assume for this course, right? Also, if you took if you took the 2101 with me, I also kind of use this particular BST definition. We're going to use the same code to really build up something, maybe about rotation and other stuff for this course as well. So it's really consistent implementation. I'll talk more about this setup in Java quickly. So and on Friday, we're going to do some programming exercise as well on this particular setup. So let's say we start with the BST like that, right? So the way to really set it up is for every external nodes, by definition, the height will just be 0. That's what we start with. And then let's say for this particular node, what should be its height? The definition is look at the height for both of its children, get a maximum, and then plus 1. So 0, 0, the maximum will be 0, and then plus 1, you get 1, and etc. Right? So that's so the general manner should be bottom up. You start with all the heights for all the external nodes and build bottom up to see the heights, right? And then we actually did to say, let's say given this particular tree, that's actually balanced in terms of its heights. And then we try to add one node right here, 55. As soon as 55 is inserted, I will maybe do a little bit more insertion exercises with you just to make sure you can brush up on the details. So once we have inserted this particular node here, and then we try to recalculate the heights again. And we'll find that, let's say these two child nodes, you can see one has the height 0. The other one has the updated heights 2. So the difference is now more than 1, right? So the high balance property will be violated. So that means as far as this node is concerned, its two child nodes has a high value with the difference more than 1. So we say that this node here is not balanced. Okay? It's a very important definition to grasp. So today we're going to use this definition a lot to really see how we can do rotation. And once the rotation is done, we want to justify about, number one, the high balance property is restored. It's not violated anymore. And number two, we want to make sure after doing the rotation, the tree still maintains to be a binary search tree, right? That's something we'll see, okay? Anyway, high balance property, that's something you want to be very familiar. Any question about this one here? We're good? Okay. And also make sure you do this exercise as well about inserting 63. Okay. You can take this tree over here and try, oh, actually just right here, right? I already got a copy for you. Take this copy here and then insert 63 to see where it should be inserted and then calculate it. Okay. All right. So that's from last time. All right. So let's now start from today. Okay. So I do have some background slides for you. So for some of them, I'll just go over quickly with you the detail. That can also help the tutorial exercise for later. So slide number 3 here is just about the Java code, just about the BST node. Okay, I'll just talk about it very quickly. And then I'll just show to you some quick tracing. And then we'll do insertion and deletion. Okay, let's see. So what we have is we got BST node right here. So we talk about binary tree, not really like a general tree. Okay, so we got BST node right here. Okay, that's a class, right? I'll make it a little bit bigger. So each BST node has the key and also value. So these are the only two, these are the attributes, the main attributes. So of course the key is very important because that's the one we're going to use for searching, okay? And the value itself may be duplicated, so it's only for the data we are storing. So whenever we want to do searching, we only search using the key, okay? So that's just basic about binary search tree. So key over here is really for searching. So usually when we visualize the binary search tree, we just fill out the key value so we can see the in order traversal, it should give you a sorted sequence. That's something I'll review as well. And then we got other attributes here. We got parents, we got left, and also we got right, right? So these are the different attributes. Let's take a look quickly, right? So if you visualize it at a runtime, if I have some BST node, let's say the node is n, right? And you can visualize it something like this. So first of all, you got some field called parents. You can think it go up, right? Parents. Okay, so that's the parents over here. And then you also got key and value. Okay, you got the key for searching. Okay, the key can be some value here. And also you got value attributes. And the value attribute itself may be an object or maybe some primitive, right? Depends on what you instantiate it to be. Okay, so that'll be value. And also you got left and right to build a tree recursively. Okay, so you got left, you got right here. So you got the left, and also you got the right, right? Very simple structure over here. Just got to be aware about the attributes that we are using. One more thing to say. The reason that we can build the tree arbitrarily large is because you can see here, the left and right here. The left here and the right here will be the roots of certain subtree, the left subtree and the right subtree, right? So you can think about, for example, the left over here is the root of the left subtree, which can be arbitrarily big, okay? And then you can build, okay? And this is just some comparison, right? You know, you remember back in 2101, we talked about doubly linked list or doubly linked node. You got the previous and also you got the next. But here we got a left and we got a right, but not exactly the same. So this one here is really a branching, right? To right and to the left. So it's a little bit different. I'll just mention that here. You can do some reflection exercise here. All right, so we got BST node. We got two constructors here. Either you don't pass anything, everything will be default value, or you can pass the key and value. Right here. So we've got two possible constructors. We'll see some example code in just one moment. And then you check to see whether or not the node is external. Basically, if the left and right child are simply don't exist, in that case, it will be external. That's the very definition for external node. And if it's internal, just be the negation of is external. Also very straightforward. And you got the getter and also setter for the key, the value, the parents, the left, and the right, right? Very basic definition for the getter and setter, right? So typically this will be the starter code you might be given to program anything further about BST. Okay, we can do some exercise this Friday when we get to the tutorial, okay? Any questions about this definition here? Okay, clear? Okay, awesome. Let's now take a look at some example code. Okay, just before that, let's now try to run some visual search very quickly. I just want to distinguish between two cases for you, and then we can actually see those two cases in the actual code tracing. Okay, so let's say we got the tree like this. It's a BST, right? How do you know it's a BST? Each value here is simply a key. If you try to do an in-order traversal, that should give you a sorted sequence. So if you got binary search tree, that simply means the in-order traversal gives a sorted sequence of the key value. Let me just say keys. Okay, this property here is actually very important. Later on, when we actually want to justify if the rotation is actually correct, we got to make sure we don't really violate or break down this search property. Okay, so this is actually very important. Okay, right, in order traversal A, you can say A 17, 21, 28, 29, 32, 44, and etc. It's going to be sorted. Okay. So there are two cases for searching. Either the search is successful, we can find the elements, we can find the key, or if the key we are looking for simply doesn't exist. So these are the two cases. Okay, let's see. So we start with the root right here. And we are looking for 65. Okay, that's what we are looking for. Okay, so basically we know that 65 is actually larger than 44. So we should go to the right, right? That's very basic stuff, right? So we just go here, and then we get to this one here. And we know that the one we're looking for, 65, is less than 88. So that means we should go to the left, right here. And this time we are lucky, we have found it. So this is the node to return. And this happened to be an internal node, okay, which is good. So this is a successful search. Successful search, meaning that the node that's returned from the BST is actually an internal node. On the other hand, which is more fundamental, when the key you're searching for, 68, for example, let's say here, this one here actually doesn't exist, but let's see exactly how. Okay? The search path over here is actually very important because that tells you where you may actually insert that key that doesn't really exist if you want to. Okay, I'll show you what I mean. So let's start with the root, 44. Okay, and then we know that 68 is larger than that, so we should really go to this root over here. Go to the right, and then we look at 88 over here, and we know that 68 is less than that. So we go to the left. So we are now checking 65, okay? And then this is not a hit, so 68 is larger than that, so we should go to the right. Okay, so we see 82. 82 is not the one we're looking for, but let's compare the value. 68 is less than that, so we're going to go to the left, right? So we got 76. Still not the one we're looking for. So 68 is less than this. And finally, we are reaching this particular external nodes. That means no further exploration can be done. Okay? So this tells us we should really stop here and return this particular external nodes. So this is the second case. Okay? So this is the second case where the search is unsuccessful. Unsuccessful search. And external nodes is returned. Okay, you can think about there might be some reference to this particular node, and then we just return that. Okay, so why is this node specifically should be returned? So if you think about the following, we're looking for 68, but 68 doesn't really exist. But what if we want to insert the 68 into this BST? The external node return over here is exactly where this 68 can belong to without breaking the search property. Okay, I'll write it down. Okay. If the non-existing key, the non-existing key 68 is to be inserted, this external nodes is where it belongs to. Okay, let's do a little bit of informal justification. Okay, so let's say this. Let's now, we don't need to see the whole tree. I just want to show you a part of it, right? You can see some intuition. Okay, let's say we look at just this part of the tree, just this part. Okay, just this part. Just this part, okay? And then let's now try to see, and this is also some kind of like a warm-up exercise for the rotation that we're going to do later, okay? So let me just give some name to each one of them. So let's say this is this is N1. N2, N3, N4, N5, N5, and also N6. Okay, let me just in case you're taking notes. N1, N2, N3, N4, N5, and N6. All right, so these are the external nodes. Let's say we are trying to do some in-order traversal of just this part of the tree. Basically, in-order traversal of the subtree rooted at 65. Okay, why don't we do that? Okay, so I'll put it here. If I try to do the in-order traversal of this particular tree, right, I'm going to get, first of all, N1, followed by 54, followed by N2, and then followed by 65. Agree? Okay, that one should be kind of a natural exercise to you. And then we go to N3, and then we go to 76, and then we go to N4, and then 80, and then we go to N5. Okay, let me write a little bit better. N5, and then we go to 82, and then we go to N6. Yeah, sorry, just running out of space. I cannot write in a single line. But you see the idea, right? We got an in-order sequence. So this sequence over here is somehow sorted, right? And what's really returned from the previous search is really the N3 right here. N3 right here. And if you think about, if we simply turn the key of N3 right here into the unsuccessful search to be 68 right here. Right? If you put it here, you can see the sequence remain to be sorted. You can see 65 and 68 and then 76. Right? In that way, we're still maintaining the order. Okay? So later on, when we actually talk about insertion and deletion on the BST, always you want to take a look at what's the in-order traversal and what's the corresponding insertion or deletion we are trying to do on the sequence. Okay, let me just recap very quickly, right? So what you want to think about is, look at this particular subtree and think about what's its in-order traversal, including the external nodes right here. And then the one that will be returned for 68 is actually N3 over here. So if we replace the N3 here by storing 68, we still get a sorted sequence, 65 followed by 68 followed by 76. So we are still good, right? So this one remain to be sorted. Okay, so this one here, this one here, this one here, sorted. Okay. All right, any questions about this? It's more like a, like a quick review, also from 2101, because we need this, right, to understand rotation later. Okay. And then let's do this one. Okay, this one here, you got to do also some tracing yourself. I'll give you some idea about what's going on here. Okay, so this is like a Java code that builds on top of the BST node that we saw just earlier. Okay, so I'll just give you some guidance about how to see this code. Oh, the code is also available on the lecture site. I'll show you where to find it. All right, you will see that under the codes here, we got a generic binary search tree, right? So that's a starting point. Okay, so you can take a look at the BST node there. You can try to rebuild maybe another tree, etc., to do some exercises. Okay, let's see here. So the first part is about just building individual nodes. So we got different nodes here. We got different variable here is going to point to different so what we want to build ultimately is a binary search tree. So we got this is the root, left child, and then left child, right child, left child, right child, right? We got only 2 levels here. And this level 2 has external nodes only. Okay, let's see exactly. Okay. So first of all, we start with all the internal. N28 is right here. And then we got N21. Also, we got N35. N35. And also, we got external. So we got external 1, 2, 3, and 4. Okay. Eventually, we're going to get external node 1 and external node 2, external node 3, and also external nodes 4. Up to this point, we haven't really built up the connection between them just yet, which is something that's going to be done right here. Okay, you can think about this part over here. It's going to set up the relationship between the nodes. Right? For example, you can see that. Let's see just for one example. You can see N28 that's set left N21. N28, this node, set its left to be N21. You're basically setting this one here to be its left. That's what you're doing, right? So you can try to go over all these, and then you will see that we are really building this particular tree here, right? That's definitely one way to build a tree, just from scratch. You can build all the nodes as individual objects, construct all the tree nodes, and then try to link them, okay? You can think about this more like a phase 1 about node construction, node creations. And this one here is about connecting the nodes. Okay, right here. What I want to do now is to show to you about the binary search, the return value. Okay, so now we got the 2 cases for us. Okay, so case number 1, we want to search for 28, 21, and 35. You can see that 28, 21, and 35. So these keys do exist. So that means the return node will be internal. For example, if I'm looking for 28 right here, it does exist. I'm going to return the internal node that contains key 28. So that's the N28 I'm returning. All right. So let's now just note that right here. So these are the internal nodes for successful search. Okay, that one should be good enough, right? So of course, if I give you a tree that's kind of larger, you should be able to trace as well, right? So conceptually, that's clear. On the other hand, if I'm looking for, let's say, the nodes that's actually the key that doesn't exist right here. For example, 17, 23, and then 33, and 38. However, what you really want to pay attention to is this. If I'm giving to you some non-existing node, depending on how its value is going to be somehow searched in the binary search process, it may return different external node, depends, right? For example, let's just take one right here. If you look at this one here, okay, the first one, okay? By the way, the first argument here, N28, says that we want to start with this particular node, the root, to start a binary search process, okay? And I'm looking for 17, okay? Let's see. I want to search for 17. I know that 17 is less than 28, so I should really go to the left. And then 21, I know that 17 is also less than that, so that means I should go to its left. So that means this is going to be the return value, which is external node 1. Okay? And you can definitely take a look at, if we try to look for 23, it's actually going to return external node number 2 instead, right? So if you follow the search process, it's going to return different nodes instead. Okay? So exercise for you. Okay, so this will be the exercise. You want to convince yourself why a particular external nodes is returned. External nodes is returned. All right, guys, any questions here? I didn't really go very deep because that's really basic Java code. I just want to give you some guidance over here so you will be able to also trace it, right, by yourself. Is there any part you want me to dive deeper? Are you okay? Yes?
I don't know. I just find it kind of unintuitive to, you're calling like u.search on a node that doesn't exist in my tree, and it doesn't return null. You know what I mean?
Yeah.
Like from an implementation perspective, like if I want to use this tree,
right.
Like, and I call like u.search and it's not in the tree, I would expect that to return null.
It's a very good point here. Let's say this. If your BST ADT only wants to support searching process, then yes, if you return null on a non-existing key, that makes sense. However, the reason we are doing this, which we'll see in the next page actually, is because we also want to support insertion and deletion.
Right.
And as we see the insertion and deletion, they are part of the process. The part of the insertion deletion process is do a binary search first. And the binary search is going to return to you the external nodes, which it can turn right away into the node you want to insert.
I feel like I could do that without using external nodes.
But if you return null, right, then you wouldn't be, well, okay, let's, we can follow the detail later, but this is just one way to do it, right? So we want to say if you really got external node return, that's the external node you can turn into some new key, okay? That's something we'll see. But of course, if you got other implementation mechanism, you can also feel free, okay? Okay, good. Okay, so let's now move on. Okay, so just before we do the insertion deletion, we'll do that. Okay, so let's now just quick some summary. Okay, this will also help, especially for the deletion. Okay, let me just summarize about the different some property for BST. Okay, binary search tree. Okay, right here. Okay, let's say we have the root over here called P, parents. And then we got left child, and we got right child. So following the left child, and following the right child. Over here, right? So we may have some further subtree down here, right? Arbitrarily big. So we got left child and right child right here, okay? So here, let's say this is another binary search tree right here. So it's called LST, left subtree. And this one here is just another binary search tree as well. It's called a right subtree. Oh, let me draw better. Okay, this will be the right subtree. Okay, so far so good. And of course, if you want to do some in-order traversal, we know that it's going to be somewhere LC and P and the RC, right? That should be in that order. But let's go for other special nodes as well. This can also help for later. So let's say I want to identify the leftmost node of the left subtree right here. Let me call that N1. Okay, and then I want to have another node here. This will be the rightmost node of the left subtree. Rightmost in the left subtree. Okay. And we have over here N3, and then over here we got N4. Okay, you can think about N3 here. Similarly, N3 is the leftmost in the right subtree. N4 is the rightmost in the right subtree, right? So we got N1, N2, N3, and N4. Okay? So I think that these nodes, let's try to think about how they should be positioned in the in-order traversal. And then we just try to identify them and talk about some property. Okay? So if I do some in-order traversal, okay, let's say try to do that. What will be the first one? N1, yeah. N1 followed by this, LC, followed by this, followed by that, followed by this, followed by that, followed by that, right? Okay, let's write it down, right? Of course, there might be some nodes in between, right? Which we don't really care at this point, okay? So we got N1 right here. And then we got some nodes in between. And then we got the left child. And we go to N2. Okay, and then we go to P right here, the parents. And after that, we got N3. We got some nodes in between. We got the right child. And finally, we got N4. Okay, so let's now try to look at them and see, okay? Well, it's actually quite obvious, in the actual sequence. This one here, obviously, is the minimum. And this one here, M4, right here, is the maximum. Okay? And then, let's now try to look at N2 and N3 somehow, relative to P. Okay? One way to say that is something like this. N2 over here is the largest key. That is smaller than P. From the sequence point of view, you can see N2 come right before P. Guarantee N2 is smaller than P. However, among all the keys that are smaller than P, N2 is the largest, right? Also, if you look at diagrammatically, P is here. So somehow this is a left subtree. Every key in the left subtree is guaranteed to be strictly less. That's a search property. However, among them, this here, the rightmost one, is the largest one. But it is still less than this. This is important, especially when we do the deletion, we have to look after this case. Okay, we're going to do that. Okay. Guys, any question? Good? Okay. Okay, let's now just finish this one here, and then we'll take a short break. Okay, and then we'll do some insertion. Okay. And then you can also look at this one here, N3, right? It can be argued in a very similar way, because we know every key right here is going to be larger than this, but N3 is the smallest one. Everything in the right subtree guaranteed to be bigger than P. But N3 here, being the leftmost node in the right subtree, is the minimum. Right? So what we'll say is smallest key. That is larger than P. Okay, question? We're good? Okay. Let's see. So I would suggest we try to do some very quick visual example for insertion. Okay? And then I would suggest for today, we will only cover insertion, and then we talk about rotation right away. And then for Wednesday, we talk about deletion. I think that'll be better, right? So we wouldn't have to review insertion, deletion, which might take even longer. I really want you guys to see some rotation, which is completely new. Okay? So for insertion, just before I present the example, it can partially address what your fellow student question was. So for the binary search method, we don't really return null. One of the main reasons is when you return some external nodes as part of the insertion procedure, that that kind of external node can be turned into a new node right away when you actually haven't found the item to be searched. Okay, we'll talk about it. That's some code just for doing binary search. You can take a look, very straightforward. So I don't really go over them in the class, but it's a recursive method. Okay, we'll talk about, okay, so for insertion. So for slide number 9 over here, so I'm gonna let you guys study that. Slide number 9, you just talk about what's the running time for doing binary search on a binary search tree. Overall, it's gonna be corresponding to the height of the binary search tree. But the height of the binary search tree is there's no guarantee about its height. It may be linear, it might be log n. So you gotta be careful. So once we talk about rotation, that's the way to maintain the tree balance, the tree height to be balanced, like a log n. Okay, so this slide here, I'll let you read the facts. It's slide number 9. Okay, I'll let you read it. Okay, insertion, very quickly. So whenever you want to do insertion, the first step is you got to do a binary search. Okay, you got to do binary search, and the binary search is going to return to you either internal nodes if it has found the key, or it might return external node if it has not found the key. We're going to handle these two cases separately. Okay, so you can also read the slides about the different steps, right? It's kind of specified in a very clear, like a bullet point, so you can read them. Okay, I'm going to demonstrate to you about the two different cases. And the running time here, watch out, right? So when I say the insertion here, I didn't say log n. I just say big O of h, and the h is the height of the tree. Unless you have some guarantee about the height being log n, you cannot really claim that, right? So here, it really depends, okay? So let's now do very quick 2 examples, and then we'll take a short break, and then we'll do rotation after the break. So let's say we try to insert either 28 right here, or we try to insert 68 right here. That's what we try to do 2 insertions. And for case number 1, you can see 28 exists right here. But for 68, you can double check, it doesn't really exist in this particular tree. So we got 2 different cases. Okay? For case number 1, I can simply say 44, because 28 less than that, so we go to the left, 17. 28 larger than that, so we go to 32. And then 28 less than that, we go to the left. So, so here, this is the node that's returned. Okay, so this is the P that we're talking about, right? So this, in this case, we simply replace the value, in this case, Suyang over here. Simply replace the value by the arguments. You can think about each node here stores the value and the key. So in this case, we don't change the key because the key does exist. So we just replace the value here, Suyang. Okay, simple case. And the second case here, 68, it doesn't really exist, but here it's very important which external node is being returned. That's something we already showed to you in the previous page. Okay, so let's see. So we got 44, start with the root, 68, larger than that. So we go to the right. 68, less than 88, so go to the left. 68, larger than 65. So we go to here. 68, less than 82. So go to the left. 68, less than 76. So we go right here. So this is the external node that we're going to return, not null. So this means what we can do is we can now try to convert this particular node into some internal nodes, right? So this is unsuccessful search. So what we do is we are going to turn this external node here into some internal nodes. You can think about in Java, you're just going to create a new node right here, right? I'm just going to write down the whole new node, right? That new node there is going to have the 68, the key, and also the value. Let's say Una here, right? That's what you would do. You simply convert this external node here into internal node. And then at the same time, you want to make sure it has a left child and also a right child. Both of them are just external. Okay, so that's after the insertion. So you can think about every time you want to do insertion, first of all, try to make sure the key exists or not, right? Once you know, then you will know whatever case you got to deal with. Okay with this? Okay, good, awesome. Why don't we take a very short break, and after the break, we'll do some rotation. Okay. All right, so before the break, we'll review about how to do binary search and also insertion. Let's now get directly to rotation. Basically, rotation may have to be done either after a single insertion or after a single deletion. So we'll do the deletion maybe on Wednesday, so we can review then separately. I really want you guys to see some rotation. It's a pretty cool idea. Okay? So let's now skip the slide a little bit. I will go back there on Wednesday. So let's start from slide number 22. Okay, to just see some general idea what a tree rotation really is. Okay? Basically, rotation is really for you to restore the balance of the tree as soon as you identify the tree has become unbalanced. Okay, let's go over some slides very quickly, and then I'll do some drawing together with you. And then we'll do one complete example. Okay, right here. So a tree rotation is performed. So when the latest insertion or deletion has caused the tree to be unbalanced, that's when we do the tree rotation to restore the balance. And the way to really do the rotation is you have to somehow look at the node you have just inserted or deleted and follow its ancestor path somehow and find out where is the first node that has become unbalanced. That's going to be the case for both insertion and deletion. We'll see some today, right? Right, and we are going to somehow, this is an interesting idea. Rotation is going to modify the shape of the tree. However, as far as the search property is concerned, it's not going to violate it. That's an interesting bit. We're going to see. Okay. Okay. Let me just go over with you about some tree rotation, some example here. But this is just somehow in the context of some rotation, like we already know what A, B, and C's are. Okay. Let's take a look. Okay. So here you got to use a little bit of imagination, right? We're going to see a little bit more abstractly. Okay. Let me just give you some context here. Okay. We are assuming the following. Let's say we have some arbitrarily big subtree called T1, and also we got T2, and also we got T3, and also we got T4, right? Let's say we have those subtrees. Each subtree can be as simple as one external node. It could be just like that, or it could be some arbitrarily big tree, and so on, right? So that's why I just draw the triangle to say that can be arbitrary. Let's say for this particular node, it has the height h. Let's assume. The root of this subtree here is h. The root of this subtree here is also, the height is also h. And the height for this root here is also h. And the height for this root here is also h. We got h, 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 h for simplicity. Okay? So now, are you convinced the heights for their parents right here, the maximum here should be h. So the height for C should be h plus 1. Agree? The maximum and then plus 1, right? That's how we calculated before. And what about the height for B here? It's going to be the maximum between h plus 1 and h. The maximum is h plus 1. Plus 1 is going to be h plus 2, right? I'll write down this one particular one for you. The way to calculate this h plus 2 is basically the maximum of h plus 1, which is right here, and also h, which is right here, and then plus 1. And we know that maximum between these two is h plus 1, and then plus 1. So that's how we got h plus 2, right? And what about the heights for this parents here? It's going to be the maximum between h plus 2 and h, and then is going to be maximum this plus 1, h plus 3. Right? That's how we calculate the heights, bottom up. Right? Is this tree balanced? Yes or no? No? Okay. The way to see that, of course, let's talk about the difference. Right? Let's be careful here. Okay. The difference between these two siblings, the difference over here is 0. The difference between these two is 1. Agree? And the difference between these two will be 2. Right? h plus 2 and h. So the difference here is not exactly, it's not within 1. So the difference over here is 2. Okay? So we say that this node over here is unbalanced. Okay, it is unbalanced because the heights of its two children, this one here, and the root over here, they have the heights, absolute value, the difference is actually not less than or equal to 1. It's more than 1. Okay, it's 2 right here. This may be caused by maybe some insertion, in which case we have to identify the A, B, and C. I'll show you exactly how to identify them. Let's say we have already identified them. We got A, B, and C. And now what we want to do is we somehow want to keep the tree still to be a binary search tree, but we want to restore the balance. Okay? So what we're going to do is we're going to rotate the tree. So we're going to rotate. Specifically, we're going to choose the middle node. The middle node, okay? You can see I kind of bold the middle node right here, the B. So we're going to somehow rotate on B, okay? And also, again, you want to use your imagination a little bit, okay? So here you can see A, B, and C somehow is slanted to the left, right? A, B, and C slanted to the left. To store the balance, you do the opposite direction. You want to somehow rotate to the right. You're going to somehow rotate to the right. Okay? Let me draw the final tree first and then try to see if we can make that visual imagination. Okay? We're going to say rotate on the middle node. B to the right. Currently slanted to the left. We want to rotate to the right. So it somehow becomes something like this. Somehow. Okay, we'll see exactly. Before I do the rotation, let's see the very important property here. Before and after the rotation, the tree must remain to be a binary search tree. So the in-order traversal should really give you the same sorted sequence. Right? So let's say before the rotation. So before the rotation, the in-order traversal looks like, okay, so you go for T1, C, T2, B, T3, A, T4. Agree? That's the in-order traversal, okay? So we get T1, C, T2, B, T3, A, and then T4. The middle node, right here. Somehow we want to make the middle node the new root. And then we want to somehow make this part here to be its left subtree. And we want to make this part here to be its right subtree. We're going to reconstruct the tree in a way. But once we have reconstructed the tree, when we try to do the in-order traversal, we still get the same sequence. All right? Let me see it once more. Okay? So this is how we see that visually. And this is the in-order traversal, the sequence. The middle node is where we're going to do the rotation. Think about the middle node. Currently, it's not a root. The root is A, but it's unbalanced. We want to somehow make the root of the new tree B. Okay, everything follows from that. Okay, let's try to draw that. Okay, so what I'll do is let's now do the B first. If I put B right here, all right, and then I want to have right here and also right here. Okay, because I know that T1, C, T2. So C here can be the root of this particular subtree, right? So I can put C here. And when I got T3, A, T4, so A can also be the root right here, okay? So I can put A right here. So I basically got CBA. I still got CBA. Let's now fill it out. T1, T2, T3, T4. Okay? So T1 right here. So think about T1 is right here. And T2 right here. And then we got T3 and T4, right? T3 and over here, T4. That's a rotation. Basically, the middle node has now become the root of the new tree. But now the question is two things. After the rotation, is the tree balanced? If it is balanced, we're going to ask, have we violated the search property for the binary search tree? If we have, then the rotation is not good. But if we haven't, the rotation is nice. Because not only that, it's still a binary search tree, but also it's balanced. So later on, when we do any search, we'll still get log-in performance. Okay, let's try that. So answer the first question. Is it balanced? And let's answer logically. Let's try to build up the heights, bottom up. We know that for T1, T2, T3, and T4, they have their heights H, 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 and H. That one hasn't changed. H here, H here, H here, H here. Agree? What will be the heights for C? H plus 1? Yeah, because maximum H and H, they'll give you H and then plus 1. Similarly, this will be H plus 1. What about B? H plus 1 plus 1. H plus 2. Now, if you think about the difference right here, okay, let me draw better. So the difference right here is 0. And the difference between these two siblings is 0. And the difference between these two siblings, A and C, is also 0. So now, finally, is this root balanced? It is. So there is no witness of being unbalanced. So indeed, after doing this rotation over here, we still get a balanced tree. But the second question is this particular rotation, has it preserved the search property? To really see that, we're going to see what's the in-order traversal after the rotation. So after the rotation, what's the in-order traversal? Okay, let's now just do that quickly. So we got T1, C, T2, B, T3, A, T4. Exactly the same. All right. So we got T1 followed by C, followed by T2, followed by B, followed by T3, followed by A, followed by T4. Okay. Let me try to just help you a little bit. So think about this part over here is the left subtree for B. And this part here is the right subtree for B. Okay, and etc. So the in-order traversal will give you just the same sequence. So the answer to both questions here is yes and yes. The first question there is really about whether the rotation has restored the balance. Number two, the second question there is really about whether you have violated the search property. If you have violated that, it's no use for the rotation because you're not even getting a binary search tree afterwards. Right? Any subsequent search will just be invalid. Okay. So this one here, just a very quick warm-up about how rotation is going to be done in general. So you ought to be very proficient in identifying the A, B, and C somehow. And then think about what's the corresponding in-order traversal, and then be convinced about what should be the corresponding reconstruction for the tree, such that it's balanced. That's something we're going to see. Okay? We got about 15 minutes. I think we can at least do one example about insertion. Let's see. Okay? So what I want to show to you is this. Okay, so that's a rotation example we did, right? And then So this slide here, slide number 23, is just about the steps for you to do some insertion. Afterwards, you may actually have to do some rotation. I'm not saying you have to do rotation always. You only do it when necessary. Okay, let's go over some bullet point quickly, and then we'll see one example. Okay, so let's say after you have inserted some new node n, you know how to do insertion. That's something we just covered before the break. You're actually going to somehow go along the ancestor path for that new node being inserted. Go over that ancestor path all the way up to the root. If you don't find any unbalanced node, that means your insertion is pretty good. You haven't caused any unbalanced. In that case, you don't need to do anything. So case one is something you will hope, but most likely not in the test. I might just give you some case where you have to do some work, right? So case number two, that's something we're going to do together, okay? But just notice that you might have run into case number one. Maybe that should be some conditional, maybe in your implemented Java code. All right, case number two. Let me just go over some very important terms and variables, and then we'll do one example altogether, right? So let's say you try to go along the ancestor path of the node being inserted all the way up to the root. The very first node you found that's unbalanced. Notice that the very first one, okay? The very first one is you're going to call it A, okay? And then from there, along the ancestor path, A's child should be called B. A's grandchild should be called C, okay? We got A, B, and C. Okay, identify A, B, and C. Once you have done this, you're going to look at how A, B, and C are slanted. If A, B, and C slanted to the left, do a right rotation. If A, B, and C slant to the right, do a left rotation. You might be thinking, what about it slant to the left and then to the right? And then you got to do a right-left rotation. That's something we'll see as well, right? So it really depends on exactly how A, B, and C are slanted. So we've got different ways to handle. But for today, we just do one, okay? All right, so here, if they slant the same way, you got to do a single rotation. But if somehow they slant different ways, maybe left, right, or right, left, you got to do double rotation. Double rotation, we're going to see that maybe on Wednesday. All right, let's now do one example here. Okay, so I'll talk about this one. That could be a nice summary, maybe for next time. Let's just do left rotation. Okay, so now you got your piece of paper with your tablet computer. Can you first start? Let's do this exercise together, right? I'm going to do it on my iPad. Okay, what I want you to do is this. You want to start with an empty binary search tree and insert this sequence of keys, 44 followed by 17 and then 78, etc. Right? Build that binary search tree. And don't forget, all the external nodes should be like a box, right? Like how we said. And then annotate the heights for each node. Okay, that's what you got to do. How about spend about 2 minutes doing this? And then we can go over the answer together quickly. Okay, I'm going to do that on my iPad as well. Okay, in about 1 moment, first of all, I would like to show to you about the tree first before we annotate the heights, right? Done? Yeah, it is easy, right? Okay, guys, how about this? Can we at least agree? This will be the nodes. All right? Okay, good. And now, just don't forget, for every internal node here, don't forget, you may have to draw the external node right here, right? Just don't forget. This is important as part of the step. Okay, and then the next step will be to annotate the heights for each node. Okay, just take 1 minute or so. Okay, just one moment. You shouldn't take too long to annotate the heights. Go bottom up. Is this something you're getting? I hope. Okay, let's double check, right? We got 0, 0, and then we got 1. 0, 1, we got 2. 0, 0, we got 1. 0, 0, we got 1. 0, 1, we got 2. And then also we got 1, 2, we got 3. 2, 3, we got 4. And quick check, is this tree balanced? Yeah, because if you check for every internal nodes, their child nodes have their heights difference no more than 1. For example, difference between these two is 1. Between these two is 1. Between these two is 1. Between these two is 0, etc. Right? There's no violation. Okay? All good. That's how we start with. And on the slide, it asks you to do a second step. Okay? Now, based on this, I want you to do the following. You may want to redraw the tree. Might be a little bit easier. So I'll call maybe B here. So you can copy the tree. Might be easier for me to do that. It's digital. So maybe just redraw the tree. Okay? Redraw the tree with all the heights, and then try to insert 100 into the tree. And then updates the heights of each node. And the only node you may have to update will just be along the ancestor path of the node that's being inserted. Okay, I'll show you that one. So I'm going to switch to the slide. I'll let you try. Okay, so insert 100. Okay, should take you not too much, more than 1 minute. But for that one there, just for the purpose of recording, I'll just do it from scratch with you. But I just want to make sure you can do it. Okay, insert 100. Okay. If you want to insert 100, you basically want to do a binary search for 100, right? So 44, go to the right. 78, go to the right. 88, go to the right. 95, go to the right. So this will be the external node that's returned from the binary search. Agree? Okay. So once this is returned, we're actually going to insert 100 right here. So the way I can do it is by doing this, right? So I'm just going to delete that external node that's returned. And then I'm just going to say 100 being inserted. From there, I have 2 external nodes. Okay, that's the insertion. And then when I need to update the height of the tree, I only need to focus on the ancestor path. So 100 is inserted, basically focus on right here. Okay, focus on this ancestor path. So think about this is the ancestor path of the inserted node. Okay, let's now update the heights. Again, let's go bottom up. So we got 0, 0 here, and this should be 1. Okay, so here we got 0, 1, and this one here is not 1 anymore, right? It should be 2, right? So this one here should be 2. And then we got 0, 2. What should this be? 3. All right? You can see it's unbalanced already, right? So this one here should be 3. Let's keep going. Okay? And then we got 1, 3 here, and this one should be 4. So we got 2, 4 here. This one should be 5. Apparently, the tree is unbalanced. According to the algorithm that's on the slides, right? we ought to define, okay, let me just show you again the slides, okay? So what we need to do is we want to find the lowest unbalanced node along the ancestor path for the new node, okay? Let's say this. In the slides, we actually said this 100 here, okay? I wouldn't write it up, I just want to wave a little bit quickly. Here, we call this the n, okay? You will see the variable n in the slides, right? That's the node that's being added, the new node, okay? So let's now go bottom up to see where is the lowest node that's unbalanced. Okay, is this node unbalanced? Is it? No, because 0, 1, the difference is 1, right? Go up one level. Is this node unbalanced? Yeah, exactly, right? 0, 2, the difference is 2, right? So this is the very first node or the lowest node that's unbalanced, okay? Okay, let's now isolate it right here. Okay, right here. So this is the lowest node. Lowest node. That is unbalanced. Okay? Now here comes a very important thing, right? The very, let's go back to the algorithm here, and we call that A. Accordingly, we're going to find B and C. Okay? First of all, let's identify A. So this is A. This is A. The B should be the child of A. However, you might be thinking, should it be the child here or the child over here? It should be along the same ancestor path that we are following. So now, along this ancestor path, the child for A is right here. So that's B, okay? So this one here is B. And this one here is C. A, B, and C. Okay? Apart from that, so now we got A, B, and C right here, right? A, B, and C. A, B, and C, they're slanted this way. To the right. That means we should do a left rotation. We should do a left rotation on the middle node of B. I'll give a little bit guidance here, and then you can give a try before Wednesday. Okay, I got about 2 minutes. Should be enough for me to give you guidance. Now you want to focus on just this subtree here that's rooted at A. We got A, B, C, and you can think about this guy here, this guy here, this guy here, and this guy here. In this case, we're lucky because they happen to be external node, but let's handle that in a more general way. Think about this one here, this subtree. Here is T1. This subtree over here is T2. This subtree over here is T3. And this subtree here is T4. Okay? If you do the in-order traversal, what do you have? You got T1, A, T2, B, T3, C, and T4. What we want to do is to make the middle node here as the root of this particular subtree. So this is something we want to do. All right? So let me do one more thing. Right here. You can see the ABC here is exactly the ABC here. And then we got T1, T2, T3, T4. We actually got T1, T2, T3, T4, right? Let's see some quick summary about what you should do. So here, if you try to do some left rotation on B, basically B is going to become the new root right here. And then B itself should really got 2 children. It can be just A and C. Okay, let's see why. It can just be A and C, and then from there, we can also get subtrees right here. 1 here, 2 here, and 3 here, and, oh, sorry. Okay, just give me 1 minute, okay? I'm gonna wrap up, okay? This is important. Okay, so this one here can be just T1, T2, T3, and T4. Okay, so now think about the in-order traversal. The in-order traversal before and after the rotation will be identical. It's going to be just T1, A, T2, B, and then T3, C, and then T4, right? If you try to do the in-order traversal on this tree here, and also this tree here after the rotation, you will get exactly the same. Okay? So now, in order for you to finish right here, right? This is what I want you to do, maybe on before Wednesday, and then we'll go over that together in the beginning. You want to redraw the tree right here. And then you want to isolate just this part right here. And then do the rotation only locally on this particular subtree. After the rotation, B here should be the new root, and A and C, and etc. T1, T2, T3, T4, as I said earlier. Try to do that before Wednesday. And then Wednesday, we're going to look at maybe some insertion that might involve maybe left-right or right-left rotations. Okay, we'll see that maybe on Wednesday. All right, questions? Thank you. And then on Wednesday, we're going to start at 4:10. Okay, so I'll make an announcement again on Wednesday. Thank you.